We're in the process of going live. Let's give it a minute. All right, folks. So last time we talked about trees or decision trees. Decision trees were the first algorithm that were, I would say, in the class of nonlinear algorithms. Before that, all the things that we learned so far in ML100 and in the previous lectures would draw a linear decision boundary. We would draw either a straight line to fit the data, or we would draw a straight line to bifurcate feature space into two halves, or maybe three halves or four halves, partition it into multiple halves, using logistic regression, linear discriminant analysis, quadratic discriminant analysis, and so forth. I mean, and this is only true for those of you who attended the previous workshop. But the bottom line is, if you didn't, the bottom line is, we would take the feature space and we would partition it into components or pieces or subregions using linear decision boundaries, or linear hyperplanes as the decision boundary. Decision tree, on the other hand, was the first algorithm we encountered where you could make all sorts of complicated decision boundary. Now, I'm going to review what we did the last time. What we did is we started out with a region. We took the example of San Francisco Bay Area, and we said, if you look at the Bay Area, the region of the Bay Area is at the tip, like you have the Golden Gate Bridge, you have the north side of the peninsula, the north side of the bay, you have the big bay in between, and you have the financial district in pink, you have the commercial, these are the buildings, then you have the Golden Gate Park, the San Francisco's park, the Golden Gate Park, then you have the residential areas. So it's a very rough picture of what the San Francisco.
Asif, are you sharing something?
Oh, am I not? I apologize. 1 second. I thought I was. Better now?
Oh, yeah. Now we can see. Thanks.
Yeah, that goes. Yeah.
So I hope this reminds you of the example that we took. We had the Golden Gate Bridge, this bridge here. This is the north side. We all are familiar with the Bay Area. We have the commercial district, right? The financial district and the commercial district, which spans out at the tip of the peninsula and along the bay side of it. On this side, we have the Golden Gate Park. Then we have the residential area. Of course, this is a very crude approximation to what really exists, but we'll use this as our setting to illustrate how we can use a tree to do our classification process. What we want to do is we want to divide any point in this space, in this big rectangular space, and be able to tell whether it is a commercial area, whether it's a park area, trees area, or whether it is a residential area. Right? So our classes are commercial, trees, and residential. So this forms this is a categorical target variable. Now, how did we do that? We took this entire rectangle, big rectangle, in which we wrapped the peninsula, and we said, the most logical thing is to first bifurcate or partition the space along this axis, along the pick a point along here, x1 axis, and split it. And when you do that, you have a very clean separation. On the left-hand side, you have the commercial district. On the right-hand side, there's a mix-up. Well, you say, oh, well, all right, we can improve upon that. How can we improve upon that? We can do another split, the second split. And now we can say that if you do the second split, on one side will be the parks, the greenery, and on the other side would be the residential area. You say, well, that's an improvement, but we need to do further. Then you make a third split. The third split is here. You make this horizontal split, and it separates out the commercial from the residential. And likewise here, in this region, you can do one more split and you can separate out the commercial from the trees and the park area. Right? And then you can say that in a sense, you are done. Right? Now, there are mistakes. For example, in this region, you see that we have some mistakes here, and mistakes are possible. There'll always be some mistakes. So you're not shooting for perfection, but you're shooting for a classifier that with reasonably low accuracy, reasonably low error rate can tell you exactly what a point in the feature space looks like or what a point looks like. Are we together? Right? Is it a financial district? Is it a resident? Is it trees? Is it this thing? So this was the problem we took. Now, how did we go about doing it? This whole process of bifurcation, just to review, what we did is we started with the whole region, R0, this whole area of land. And we said that the first split we'll make is along the X1 axis. We divide it into this and this. So this is it, the commercial area and the rest of it. When we do that, we realize that the commercial area is a good split. R1 is a good split. We'll probably not need to split it again, but R2 needs improvement. So the next split we make is one more horizontal split to just put the greenery in between. You notice that we put the greenery in between. And we say, well, that's an improvement. And then we realize that, well, this region, R22 now that we created, still has a mix-up of commercial and residential. So we do a horizontal split to take care of that. And subsequently, we do a horizontal split of the middle region also. And so this is what we end up with. If we try to represent it as a tree, R0 split into R1 and R2, R2 split into R21 and R22, and R21 went through its split and R22 went through its split. So this entire process, if you notice, we can represent it as a tree. And this tree is called the decision tree. Of course, the sum total of all the leaf level regions is R0. Likewise, at any level, if you add the regions up, they will all add up to the original region. That's the way we want to do it. So just to review the decision tree algorithm, how do we do it? The steps were, you start with the whole feature space as R0. Then you find the best cut point on one of the axes. Now, how do you find the best cut point? You'll have to scan each of the axes to find the best cut point. So it is computationally intensive. For each of the subregions next, search for the best subregion to split and the best axis in the region. So suppose you have 3 regions, you'll have to go and search for a best cut point in each of the regions. How do you find the best cut point in any of the regions? You'll have to go to that region and scan the 2 axes here and find, is it best to split against X1 or is it better to split against X2? Whichever turns out to be better, you would go ahead and do the split and you would recurse that downwards. But when do you stop? How do you decide that we have had enough? Well, when the number of points in a region is below a threshold, let's say 10 or 100, you decide not to split anymore, right? Now the question is, how do you decide the best split point? What is the criteria? Now, it depends upon whether you're doing regression or classification. Just to whet your recollection, regression is the process of predicting a number. How much ice cream would you sell on the beach, for example? Or in this example, to illustrate or motivate using the decision tree for a regression, I took the example of an open field in a cold region. So let me remind you the example that we took last time. We took the example that you have a big piece of land, a rectangular piece of land. On one side are this cold tundra forest, right? Those of you who know about the Arctic, you have this deep, dense forest out there, the tundra and the taiga forest. So imagine that there's something like that there, right? It's deeply forested. Then on this side, what you had is you have a house and the rest of it is open field. And to motivate regression, to predict a number, we said, let's see what the temperature would be on a cold night at any point in this box, in this region. So to motivate it from a physical perspective, an open field will radiate most of its heat. So it's likely to be the coldest, right? a taiga forest or a tundra forest is likely to be dense. The trees will act as a cover, and so it will not be so cold. And finally, if there is a house, let us imagine that there's a fireplace in the house and there's cooking going on in the house. So the house is likely to be the warmest. So what would you like to do? How would you like to build a decision tree? You may start out by first splitting along this big blue line. It will bifurcate out the forest. And now you can say in the beginning, because this house is a tiny region of the field, you can say that the field is cold, with including the house, and the forest is warm. Well, that is a good split, and it works for the forest because uniformly the temperature would be the same in this region. On the other hand, in the field, we got something wrong. Most of the field is fine, but we need to box out this region because the house is warm and around the house is warm. So what would you do? You can do a split, horizontal split, to just cut out this open field of this, and one more split here to cut out the house. Now you have boxed out the house region and you have a tree. Now, this tree is a perfectly good tree. You could perhaps optimize on it by erasing. For example, you could erase this. I'll just put a marker here. No, let me take a red marker. Hang on. Please give me a moment. This tool doesn't quite work very well with Zoom. It tends to, let me see if I can, by the way, guys, give me a moment. Let me see if I can bring all the tools to the side instead. If there is a feature to do that. No, it won't allow me to do that. All right, be as it may. Let's use this. So suppose we use, oh goodness. Let me try if I can move the controls instead to the side. Hide, float. Meeting controls. Okay, we'll do like that. You guys can all see my screens, isn't it?
Yes, no problem.
Control, Alt, Shift, H. I should remember this to get it back. So what you can do, if you think about it, this particular part of the segment, if you remove it, you realize that you will get a simpler tree, isn't it? I'll just draw that tree here. You would get a region split like this. Big split between the green and the forest and the open field, and you will get a split like this. Do you see that, guys? So you will end up with non-rectangular region. This is your field. This is your house. And let me just say open field. And this is the trees. Open and house. And this will be your best decision tree that you can build, and that would be quite useful. But let's stay with that unpruned tree and ask ourselves at each given moment, how do you find the best? To get a simpler tree. Please say that again. Just draw that tree here. You would get a region split like this. Sorry, guys. For some reason, I'm hearing my own echo back. Are you guys also hearing my echo back, or are you guys on mute? Okay.
I heard one fragment.
Yes, I think somebody was listening to YouTube at the same time is dialed in. So you'll have to mute your YouTube, guys, if you are. You have to be on one or the other. All right. So now the question is, how do you split? To split, you need a mathematical measure. Now, here are the rules of the game. So we are playing a game here. The rules of regression is, and in any region, what is the value here for this thing? You have training data. So you have temperature values for all of these data instances. You take the average temperature, right, of this region, R2. You take the average temperature, and that will be the prediction for temperature in the forest. Likewise, you take the average temperature in each of these regions, and you take that to be the prediction. So if that is your prediction, you can quantize your total errors by taking the value of the actual value, subtract the average from it, which is your prediction, and the gap is the residual. So far, so good, guys. Any doubts about this? By now, this should look pretty obvious, right? Our errors are the gap between prediction and reality. You predict the temperature to be, let us say, 30 degrees. It turns out that the forest was actually 18 degrees and 18 degree Fahrenheit. So you do have a gap. You got it wrong by 12 degrees. And the total error is the sum of square of these mistakes or the errors. So where would you like to split? You would like to find a split point that splits the region into subregions such that this E is minimized, isn't it? You want to find the point at which if you split, you would have the maximum reduction in errors. Because if you take a region, big region, initially it will be the average of the entire region. If you split it, you will end up with two different averages, this and this, and the sum squared errors will be better because this is warmer in general, this is colder. And so the cold will have a cold average, the warm will have a warm average. And so you will be closer to the true value of numbers here and the numbers here. So this will help you determine the best split point. Are we together, guys? So this is what we talked about last time. So we use that to compute the errors for regression. So regression is straightforward. You use the sum squared errors, which you are familiar with, to find the point of maximal gain, maximum bang for the buck. Where should I split so that the errors get reduced maximally? Any questions before we continue, folks? We are reviewing last time. Now let's move on to classification. Suppose I convert this into a classification problem. I say any given point X, let us say point X in the feature space, this point, you have to tell, does X belong to that point? Is an open forest, is a house, or is a, well, open land, or it is a forest? Which of these three, open field, which of these three does it belong to, right? So how would you go about doing it? You have some training data. The algorithm sees some trees, has been given some answers. What could it do? It could just take the training data and say, where should I split so that I get as pure a split as possible, right? Or one way to think about it is that if you look at this entire region and you take the majority, let us say that the majority area data points happen to be white, right? The open field. And let me color the house with a different color. Let's say that the house is this colored. So what would be the majority here? You would look around and say most of your data points, let us say, is the open field. So if I were to ask you any point before you split the regions, what is it? Your answer would be the majority. So you would declare every point to be a open field. Well, if you declare it to be the open field, you'll get it wrong here and you would get it wrong here. So you will have a lot of mistakes, isn't it? So what you do is you look at the proportion of mistakes here. So you would have the proportion of points that are open, which would be the proportion of correct answers. You look at the proportion of points that were actually trees, that would be the proportion of errors, and house, that also would be errors. So what you would end up is a proportion of each of the classes that will help you realize how many correct answers are there. So for example, the proportion of open points are correct, proportion of errors. And what can you do with proportion? You can say, hey, let us play with proportions. You want to find a split per point with the lowest proportion of errors. Generally, proportions are not used. They're crude measures. They're not well behaved. So what you use are slightly sophisticated mathematical tools. Those tools are called impurity indices. Those are Gini and entropy. Now, Gini and entropy are both interesting functions, I think last time in the review, some of you said that you were not very clear about G1 basis and the information gain graphics is covered. In the same genre, guys, I'm getting, is that a question somewhere? Arini, were you asking a question?
No, Asif.
Okay.
Sorry.
So we have this impurity index, and the feedback I noticed in the polls was that we didn't quite understand it fully. So what I'm going to do today, before we continue on, I'm going to give some time to explain it all over again, and then we'll come back and review these notes. Is that fine, guys?
Fine by me.
All right. So let us go and look at, before we do that, let's do it very simply. Let us consider a function x, right? And let us consider a function g of x, and x belongs to the interval 0 to 1. So in other words, it's some sort of a proportion. Proportion of any point, any type, any class, let's say open field or trees or house points, would be as a proportion of the total, it will be a fraction between 0 and 1, right? So it will belong to this interval. Now let's the Gini be x. Let's consider the mathematical function x1 minus x. Are we together? And I'll also consider another mathematical function. Let me call it entropy is minus x, natural log of x. Are we together? So we are going to forget about all decision trees and all of that. We are going to study the mathematical properties of these two functions. What do they look like? These sort of functions actually are very, very useful in machine learning. You'll not only see it here, they are fairly ubiquitous in the landscape of machine learning everywhere. So let's study it. Give me a moment, guys. I'm having a sip of soda here. So let's take the unit interval from 0 to 1. And here I'll go very slowly, guys. If you don't understand, please do stop me. Let me draw, and this is the unit. So this is x-axis, and let me draw G with, well, let's use different colors for this. I will use G, blue for G, and I should use, let's say I use this color for entropy. Let's make it a little bit thicker. Okay, much better. Sorry. Are we together? We use this. So let's see how this behaves. You realize that when x is 0, G will be G will be 0, isn't it? If you substitute 0 here, what will you get?
0.
0 times 1 is 0. On the other hand, when x is equal to 1, what do you get?
0.
Once again,
0.
you get 0 because this term will go to 0. And so now if you look at this function, it's very interesting. Those of you who know calculus can just directly do it. You would know that G prime, that is dg dx, and you don't have to know calculus, by the way, is equal to, what is it? It is equal to 1 minus x,
Minus 2x.
right?
1 minus 2x.
Minus x, right? And if you set it to 0, so if you want to find the extrema, you have to set the derivative to 0. dg 0 is equal to dg dx is equal to 1 minus 2x. Implies x is equal to a half, isn't it? And if you take the second derivative of this, d square g dx square, you will easily realize that it's minus 2, implying that this is a maxima. When the second derivative is negative, you know that it's a maxima, right? So this is a bit of calculus. If you don't know calculus, no harm done. Just try to put in a lot of points between 0 and 1, and you can convince yourself that whatever happens, this thing has to be symmetric. So this thing will have to go. Did I make it symmetric? Oh, almost there. Let me try again. Let me like this and try to be a better artist. No. Oh boy. Almost. So let me try to be, oh, so just pretend that it is symmetric. And I got it right? This is how GX would look. So in other words, it will achieve a maxima at half, right? So this is interesting. We will see what it is trying to say in a moment. Let's look at this entropy function. So G, the word people often use for that is Gini, but you don't have to pay attention to the word. Let's look at this, the entropy function, right? This entropy function also behaves like this. It sort of behaves like it is just a more, well, this is terrible. This is anything but an entropy function. Okay, let me just be a little bit smarter. There, that's better. So it just rises up a little bit quicker and well, it doesn't look quite symmetric, but you guys are better at entropy. Entropy, and this is G of X. Are we together? And this is, so far so good, guys. Is it easy to understand? Anyone who's having difficulty understanding this, this is a great moment to stop me. We are good here so far, right?
Asif, yeah, can you explain it again?
All right, I'll explain it again. See, look, I'm just drawing ordinary single variable functions. Look at this function, x1 minus x, right? What does it look like? What is the shape of that function? It looks like the blue line here, right? Does it look like the blue line to you, Anil?
Yes.
It would look like the blue line. And now look at the this function. It looks like this. Now, why it goes up a little bit over, it will take you a while to see. See, we can see that. If x is 0, what will the entropy function be? 0 times, well, log of 0 is minus infinity, but we, as a convention, believe that this is 0. Now, why is this 0? It's a little more complicated. It is called the L'Hopital rule. Means whenever you have a peculiar situation like this, what you can do is you can take the derivative of this in the limit. You can do limit epsilon tends to 0 of like, well, okay, x tends to 0, x ln x log of x. And if you're trying to do this, you can take the derivative of these terms and you can convince yourself that this will all go to 0. I'll leave that as an exercise for you, but take your interest. When x is equal to 1, this term will be 1, but log of 1 is 0. So it will come down here to 0. So it's basic, you know, the sort of pre-calculus stuff. And if you again take the derivative of this, so let us do that. I'll do that here. D is equal to minus x, right? Minus, what is it? What is the log of x? Do you guys remember?
1 over x.
1 over x minus x, right? So here sorry, first term you would have is minus log of x. And the second term would be minus x over minus 1, isn't it?
Yeah.
And so you would essentially come to the conclusion that suppose you have this. Oh, by the way, this is not, I made a mistake. Typically in, you take the natural log for entropy, but in machine learning, you actually take it to the base 2. My mistake, huh? Log to the base 2. So log LG to the base 2. If this is equal to 0, you are saying Lg to the base 2, log to the base 2, x is equal to 1. So what is x?
2.
X is equal to minus, so this is -1. So x is equal to a half. So it again achieves a, at a half, it also achieves a maximum, right? This statement is log x is equal to -1 if you look at this. So is it any better, guys? Are we following it a bit more? Anybody who wants me to explain it again? Anybody who didn't get it?
Me.
So guys, remember, when we do decision tree, today is the theory day, this ensemble and so forth. A theory is something you learn only once in your life. It is worth understanding it. In practice, you won't be using the theory. You remember that when we write code and do the machine learning practical exercise, you can actually do it without understanding the theory. But after some time, you hit a roadblock because you won't be able to think through your data unless you know the theory. So theory is good to understand, but practicality is somewhat a different set. There's some intersection, but it's a different set. Okay? So any questions, guys? Huh? Anybody who didn't understand, please be frank and I'll repeat again. Or tell me which part you want me to explain and I'll explain again.
So Asif, both Gini and entropy, like they are used to know the impurity index. So what is the differences between them? Can you please explain?
Yes, and in fact, I'm coming to that one now. Thank you for asking that question. So now, we did this exercise in the abstract. Let us bring this exercise to the ground. What is X? Now, let's relate it to this bit of mathematics. How do we do that? Let us say that, and the definition of Gini, and I'll again use G, Gini, G index, impurity index. Our G impurity index is defined as that. For each class, so suppose you have a region, right? In the region, there are certain points, then there are certain house points, where the house is there. And then there are certain green points. These points are all green. And obviously, I'll just exaggerate the quantity of white points. So you see, let us take some number. Let us say that the whites are the open field points. Open field points are, let me take 60, not 60, 50. Let me take them as 50. The tree points, forest points are 40. The house points are 10. Are we together? There are 10 yellow points, 40 green points, and 50 open points. And they all add up to a grand total of 100. So now, what is the proportion of open here? It is 50 over 100. The proportion of forest points are 40 over 100. And the proportion of house points are 10 over 100. Would you agree, guys? Right. And now from this, let us derive for each of these quantities. Oh, sorry, what am I doing here? Something weird happened. Oh, this 100. And let me get rid of this point. Well, the eraser doesn't seem to be working. I'll leave this line here, apologize. So, oh, all right, we'll go back to the points. So now, suppose I compute the Gini, the G of open points. Just take the proportion of open points. Remember in Gini, the formula was Gx was x1 minus x. But there are 3 of these x's here. Let's do it for open points times 1 minus proportion of open. Proportion of house points times 1 minus proportion of house points, and proportion of forest points times 1 minus proportion of forest points. So you guys are all good with numbers. We can compute that. This is a half times a half, isn't it? This is a fourth. This would be house points are 1/10 times 9, isn't it? So that would be 9 over 100. And this would be 1/10 times 9/10, isn't it? So this is equal to a half. This is equal to 4/10. This is equal to 1/10. So 1/10, 1 minus 1/10, and that is equal to 9 over 100. And what would this be, the forest? It would be 4/10 times 1 minus 4/10, 4/10, and that would be 6 times 4 is 24 over 100, right? So I might as well make it 25 over 100 just for uniformity. Are we together? Now, does this make sense, guys? So now what we can do is the Gini impurity indexes index of this entire region before we split it. This entire region before we split it is the summation of all of this. Sum over each of the classes, each of the I, Pi, 1 minus Pi, right? So it means we add up these things. If you sum it, it becomes equal to 25 plus 9, 34, plus 24 is 58 over 100. Does this make sense, guys? Are we together, guys? Right? So we say that this is 0.58, right? Or 58 by 100. Right? Are we together? Gini value is this. Does anybody need clarification with this? Bhuvna, I'll come to your question. Huh? What's the difference between the two? I remember that. So far, so good. Are you guys getting it? Anybody has a question? Now, I could have computed this for the entropy also, but let us not, for the time being, do it. It will be a repeat, just here doing it with log. Right? Now the question is, where can we split? Let us say that we split this region. Let me redraw this region because we have come down here and we'll do the computation again. So this is a region. These are your white points. These are your yellow points belonging to the house. And then these are your forest points. Maybe I'll make the white also a bit more pronounced. Let me take this. All right, guys. So the question is, where should we split? I'm deliberately going to take us. So intuition tells you that we should split, let us say, at this point. What just happened? That wasn't very illustrative. Let me take yellow. Well, Not useful. Okay, let me try again. More colors, saturation, red. That also didn't help. Well, highlighter doesn't seem to be the right thing to use. I will use a color. Let's use blue again and use a thick version of blue. So would you agree that this intuitively makes sense as the first good split? Would you agree, guys?
Yes.
Yes.
And let us see why our intuition is telling us to do this. Now, if you do this, we end up with two regions, region R2 and region R1. Now, you notice that R1 is not a pure region, but R2 is a pure region, isn't it? So now we'll have to do the same analysis that we did across the two regions. So we do it for R1 and R2. R2, what is the proportion of open points in R2? 0. What is the proportion of houses in R2?
0.
0. Proportion of forest in R2?
1.
Well, all 40 points are here. There are 40 points and all of them are forest points, isn't it? So you would say it is 1, right? So now see what will happen. If I do 0, 1 minus 0, 0 times 1 minus 0, the same thing, x 1 minus x, right? Or the p, or let me write the formula in terms of proportions, a p 1 minus p. And here it will become 1, 1 minus 0. And when I do the same summation for R2, what is the summation coming out to be? This is 0. This is 0. And what about this, guys?
Last one will be 1 minus 1, I think.
Oh, sorry, 1 minse 1. Thanks, Avijay. Thanks for correcting. And what would this be? Also
0.
And so what is the impurity on index on this side?
0.
So Gini of R2 is equal to 0, isn't it? And this is the Gini of R0, the initial. Now, region. Now let's do the same thing. Proportion of forest here is very easy, 0. Proportion of open points is, well, how many points are there? There are 50 white points and 10
50
yellow
to 60.
points, 60. So this is 50 over 60. And this is proportion of houses is equal to, how much would that be, guys?
10 over 60.
10 over 60, excellent. And so once again, let's do the P1 minus P part. When we do that, 0 times 1 minus 0, 5/6 times 1 minus 5/6, and this would be 1/6 times 1 minus 1/6. So this is equal to 0. Oh, sorry, this is equal to the second one. This is equal to 0. Would you agree? This is equal to 1 minus 5/6 is 1/6. So 5 over 36.
36.
This would also be equal to 1/6 times 5/6 is 5 over 36, right? And so if you sum it for region R1, what do you get? You
10
get
over 72.
a 10. A 10 over,
Sorry, 10 over 36.
are we together? And so now let's ask this question. Was the split worth doing? Let us ask this question. What was the initial Gini before split? That is sigma R0 is equal to 0.58. Do you remember, guys? We computed that here, right?
Yeah.
We computed it right here. This result. And now after the split, R1 plus R2, what is it? We are adding a 10 over 36 plus 0. Isn't it, guys? If you notice, this is 10 over 36. This is 0. And so what does that come out to be?
0.2 something.
10 over 36. This is approximately equal to, would it be fair to say that this is approximately 0.3
Yeah.
or less, actually 0.28 or something like that?
Yeah.
Right? If one of you were to pull out your calculator, you would see that it's something like that. So now, so the total Gini, has it decreased or increased?
Yeah.
You're comparing 0.58 with 0.28, which is smaller. After the split is smaller, isn't it?
Decreased.
It has decreased. So this decrease between the Gini before and the Gini after is called information gain. So you say information gain is defined as by definition, this is a symbol of definition, is measure in impurity before minus impurity after. I use the word impurities because you have two regions now, R1 and R2 that it's split into. So the difference between the two, therefore, is up here is equal to here. It is 0.58 minus 0.28. And that is equal to 0.3. Approximately. I don't know what these values are. You can plug it into the calculator, what 10 over 36 comes out to be. 0.3. This is greater than 0. Would you agree? So what you do is you compute this 0.3 and now, well, okay, I'll just mention it that it also happens to be greater than 0. Now, you ask yourself, look at this picture and ask yourself, if you had done the split anywhere else, would you have gotten a better split? So for example, if I had done this split, I won't go through the full calculation, but ask yourself, if I had done this split instead, a horizontal split between the above and the below, would that have been better?
No.
You can literally see that there would be much less pure regions that get created. And so you would say that the information gain would not have been as much. Are we together? And that is why, and I'll remove this, red region from here. Oh, sorry. Red region from here. So this also, well, let me get back to blue. So this is it. So do we understand the concept of information gain now, guys? Is it any better? Let me know, otherwise I'll explain it all over again. We will never come back to the theory of decision trees again. So it is important that once in our lifetime, we understand it. Any questions, any doubts? Anybody would like me to repeat? Anil, are we clear now?
Yeah.
Okay. So guys, what exercise I repeated for Ginny?
Asif,
Yeah, go ahead.
I'm sorry. I just have one question. So this impurity gain over here, like the differentiation was very easy since we didn't have as many properties or qualities. Let's say, for example, an insurance company wants to, or either a bank wants to give out a loan, and they have certain criterias. So there would be n number of criterias which they would want to have. So in that scenarios, would the information gain will be as clear?
See, it can always be computed is the answer. How? Here we have two axes, right?
Yeah.
This is one, x1, and this is x2. So what we're doing is we're scanning for the best cut point along x1, the best cut point along x2, and theoretically, we are finding the information gain for every possible cut points. As you can imagine, there are infinitely many cut points on x1, infinitely many cut points on x2.
Okay.
Right? Theoretically speaking, we are doing all of those cuts and finding where the information gain is maximum. which cut point gives us the maximum information gain, right?
Okay.
Though in practice, the mathematics kicks in and you can be way smarter.
Mm-hmm.
You don't have to do infinitely many computations, right?
Okay.
But we won't go into the technical details there. You
Right.
can. So now generalize from this. This is
Mm-hmm.
two-dimensional. So
Mm-hmm.
suppose the bank has, insurance has 50 features.
Mm-hmm.
Yes, you'll have to scan all 50 axes
Right.
and find the best cut point along each of those and look at the best information gain that
Mm-hmm.
happens by cutting at any point along any of the axes, what it will be. So you're really looking at a massive computation, which is
Okay.
why decision trees used to be, in its days when it came out,
Mm-hmm.
considered a brutal computation. Right?
Okay.
People would find all sorts of clever ways to make it faster, better, more efficient. Right?
Okay.
So the algorithm of decision trees, therefore, is pretty sweet, actually. The internal implementations. See, one part is the theory, another is the numerical implementation. So there, people have found clever tricks to make it faster over the years. And so 50 dimensions is no big deal these days.
Yeah.
So Asif, I have a question here.
Please go ahead, Abhijit.
So here basically we intuitively we could see, so we drew the line there between the green and the white, the open field and forest, right? Now the computer, how would it do? Basically, it will start from 0 till the end. How will it know from
It
where
will
to
go from,
start and where to end, and what should be the increment?
see, it starts from 0, 0, right?
Yeah.
It goes along the first axis and finds the best cut point.
Mhm.
Then it goes along the second axis and finds the best cut point. Then it goes along all the axes. And then it finds at which of these cut points give you the maximum information gain.
So the in a particular axis, when it is scanning, where it has to end, it will basically know from the range of that variable.
Not only the range of them, it's actually cleverer than that. See, what happens is that at some point, you notice that impurity decreases and
Okay.
it starts increasing.
Right.
Right?
Mhm.
And so you observe, you know all of those points. You can easily find the minima of where should I split to get a minima of the impurities. So
So
it
computer does that basically. It automatically stops basically.
stops, yeah.
Okay.
Right? So there are heuristics like that. See, you have to be in highly nonlinear situations. You still do have to scan it multiple places, but
Yeah.
there are ways to quickly do this these days, right? So that gets into the internal details of a numerical implementation of
Yeah, exactly. That's what my question is. Okay.
a lot of depth. See, all of these algorithms, when decision tree came out, it was slow and sluggish, and then people improved it and so forth over the years. So the cart, we call these cart, classification and regression trees.
Hmm.
There was cart 1.0, there was cart 2.0, 3.0, etc., 4.0, then 4.5. And then those guys decided to just, I think if I remember right, they tried decided not to open source it, but take it commercial for some time. Some of those guys, they made it cart 5 or so forth. Then open source caught up and so forth. So obviously there is a lot of deep numerical work that goes in perfecting these algorithms.
Yeah.
And a lot of these are done at the level of C and Fortran. Right? So because there it runs much, much faster. C, C++, Fortran is where you implement it. There is a Java implementation also. Weka has a Java implementation of the cart. I believe they do cart 5 or cart 4.5. I don't remember which one of the two. If you're curious about that, all of this code is open source, remember.
Hmm.
You can go and look into the code, but be prepared that, it represents some 20, 30 years of accumulated optimizations, isn't it? So the code it will take you a while to catch on to the code. In broad strokes, you'll get the code immediately, but to understand the subtle optimizations, it will take you quite some time. Any one of you here have a background in numerical computations? or Fortran? Am I the only Fortran guru here?
What is the latest? What is the latest Fortran, Asif? I remember I heard like
I
we used to do
worked with
Fortran
F90.
4.
Yeah, I worked with F90. I don't know what the latest is.
Mhm.
But in my generation, we were writing Fortran. Yeah, F90 is, I think, still that. See, I still write sometimes. Actually, what am I saying? Only recently I wrote Fortran code. So I think I use the F90. You use that open source thing, right? That Linux comes built with.
No, I used Fortran long back for that modeling and simulation, the control systems.
Yes, yeah. It's a
That was Fortran 4, I think I used.
yeah, possibly. Yes. It
Fortran
is.
95 maybe.
It's 95. Huh? Okay.
Yeah, we used it in computer-oriented numerical methods type
Exactly. Yes.
subject. Yeah,
It's a very simple method,
it is very simple. Yeah.
and the performances are absolutely nothing can come close to it.
But it was meant for mathematical operations. I'm not sure if anything, it evolved into other stuff, but
No, it is safe for scientific computing. And even today, you would be surprised that most of the scientific computing is done in Fortran. When you are doing it and you think you are doing it in Python, if you observe very carefully, what is happening is when you install the Python scikit libraries and so forth, it is actually installing Fortran and Fortran libraries. So it is actually utilizing all those highly optimized Fortran libraries in the background. Fortran and C libraries in the background. All that BLAS, LinPack, LAPACK, Atlas, and all of those are heavily being used because they have 40, 50 years of evolution behind them. All right, guys. So this is, do we feel we understand the concept of information gain better now?
yes.
All right, guys. So with that, let's go back and review, and then we'll move to ensembles. Remember, today's topic is ensembles, but we always give an hour to reviewing the previous week. So this is it. Now, entropy is just another measure of disorder or impurity. Entropy, literally the word is disorder. Entropy has been well understood and studied by physicists, for example, Gibbs and so forth, the thermodynamics and statistical mechanics, or well studied more than a century ago. It made its way into computer science with the work of Shannon and information theory and so forth, where he brought it into, the whole encoding aspect of it. And entropy is all over machine learning, right? It's always a measure of disorder. The underlying belief is that if you look at the data properly, you can observe it in a way that you see the least disorder, right? You can things like that. So obviously there is some disorder in the data, inherent data, but if you look at it, for example, if you look at it, let's get back to our example. Here, if you split on the big thick blue line, you realize that you have created more order now. Green points on one side, white and yellow points on the other side. Right? If you think of them as gas molecules, green gas molecules and white gas molecules, they are well compartmentalized, isn't it? Whereas if they are all mixed up, then that's a state of disorder. That's a basic thinking there. So now let's go back and review everything. Now it should be very easy, hopefully, to do. So we go
Asif,
about, you go ahead.
I see one final mathematical question there. Why is it base 2? Is it because you're always splitting the regions by 2?
No, please say that. Why is it always?
You said that it is actually not natural log, it is log base 2 for the entropy.
Oh, you could actually, here's the thing, log 2 or natural log, right? It doesn't matter much. Computer scientists tend to take the log 2.
Okay.
Right? You can take the natural log, actually.
Okay.
That would be interesting. Right?
Yeah.
It would just lead to different split points and so forth. Slightly. So the thing is, now to Bhuvane's question, which is better, Gini or entropy? Which of these should we use as a measure of disorder? The answer to that actually is no one knows. Do you like that answer, Bhuvane?
Uh,
So
I think both are same.
yeah, no, there is actually a deeper thing I keep speaking about. It's called the no free lunch theorem. What it says that in the absence, no one algorithm or approach is ever better than the other. On average, data rules. So data will occasionally prefer and give better results for Gini, and sometimes it will get better results for entropy. Gini used to be very, very common long ago. Entropy came later. A lot of people swear by entropy. They say in general they find better results with entropy in their domain of knowledge. So it may so happen that for the problem that you're solving, let's say that you're working with specific, you're making classifications with respect to some chemicals, right? And so on and so forth. There, or in your situation, one may be more effective than the other. Case by case basis. You'll come to know only when you do it. However, the gap is not too much. If you just replace Gini with entropy or vice versa, the small gain in model performance, it will be small gains. You're not talking about big, like these are small potatoes, right? These are not big deals. You won't go something like from 30% accuracy to 90% accuracy. I can't imagine a situation where just flipping the impurity measure would give you such drastic improvement. You might go from 82 to 84% or 86% improvement, right? And you know, a model that has gone from 82 to 86, just free, without doing anything, without any effort, just changing from Gini to entropy, which in code is just one word change. Well, why not get that 4-5% extra performance, isn't it? So that's what it comes down to, which is why you should always experiment with both. Now let's go back up and finish our review. So I said you review the region into parts, right? We got the concept of entropy. This is what we talked about last time. After that, now that we know this stuff, we talked about the fact that when you build decision trees, we can do pruning of the tree. Why do we do pruning of the tree? Because sometimes when you go down and build the tree, your tree becomes inordinately complex. And pruning of the tree is regularization or simplifying the model. And when you simplify, I won't go into too much details, but there are techniques so that you can get non-rectangular boundaries. You know, for example, here, if you imagine that this line was there, and now you erase this blue line, so you got a non-rectangular boundaries. Right? So pruning of the tree, another question is that how is it that you can prune the tree and get better performance? And that question is worth answering. You won't get better performance on your training data. Training data would prefer an unpruned tree and give better results. Where will a pruned tree give you better results? Can you guess, guys?
On the inference, or
Yeah,
Can you
on
repeat?
validation data. So if you take the data and you split it into your training and validation data, what will happen is training data, it will overfit. But on the validation data, you check that if I prune the tree this way, does my performance improve? And you will notice that by pruning the tree, your validation test results, your results on the validation data will improve. And that's how you know you're improving. And you keep on pruning till you realize that it doesn't improve anymore, it becomes worse, and you stop. Are we together? And remember that it's the same thing as the bias variance trade-off. You need to find out a model that is too simple is biased. A model that's too complex, it has variance errors. So when you start at the root, you have high bias errors. You have one big region. Then as you recursively keep on splitting one by one, you go and remove bias errors, but you're making a very complex model and you start developing a lot of variance errors. So you need to backtrack now. You need to return, remember let me just give you the idea of the bias variance trade-off. This is the bias errors. It decreases bias errors, right? And then the variance errors on test data would be, let me use another color. Let's say that this is the variance errors, complexity errors, right? Remember we talked about it. And so the total error, which I should depict, I suppose, with the red line, is this. So what happens? When you make the model very complex in the learning process, you end up somewhere here, right? Here, if this is the complexity, you have ended up with a very complex model. So what do you need to do? You need to backtrack. You need to get back to this point. This is your prune tree.
Mm-hmm.
Right? You need to prune and step back in complexity till you come, but you don't want to over prune the tree, because then you'll start gaining into, so you need to come down this path to this point, but you don't want to go back up this. You want to stop here. Am I making sense, guys, about pruning of the tree?
Yes.
That is the purpose of pruning the tree. That's all it is. That is what it means to prune the tree. And so a review of trees finishes. I would like to now move on to ensembles. Ensembles I talked about as the wisdom of crowds. There is actually a theorem in mathematics that was discovered a long time ago. It says that if somebody's chance of guessing an answer is just a little bit more than 50%, right? So in other words, the person is a weak learner, or just about slightly gets it more right than wrong. Then in a systematic way, you can harness the wisdom of crowds. You can take a lot of these weak learners and, excuse me, you can create an ensemble, a crowd of these. Then you can aggregate their wisdom. How do you aggregate it? If you are doing regression, so suppose you want to ask people, like I did, like I told you, I used to do that in class. When we used to physically meet in the before COVID world, I would give you guys a jar of stones and ask you to guess how many stones are there. Invariably, almost everybody would be wrong. Maybe one or two people will be close to the right answer, but the average of those answers was uncannily close to the right answer. The reason for that is all of us have a bias. We have certain information in our decision and certain bias, right? So we may guess either optimistically or pessimistically. But then as you add up everybody's answers and average it, the average of the errors cancel out. But the average of the information remains the information. And so the right answer begins to stand out. That is the wisdom of crowds. Now, why weak learners? I talked about this thing that weak learners are better than strong learners. It turns out that strong learners have a higher tendency to get correlated with each other, entangled with each other in their decision making. So in other words, they begin to think alike. When two learners are thinking alike, they are redundant. You can just use one rather than two, right? So for example, if you need to get an understanding of whether there's global warming or not, the last thing you want to do is get two members from the same think tank, right? Because all the members in the think tank have been looking at the same data and coming to the same conclusions. So either both of them will strongly favor the statement that human beings are causing global warming, or both of them will strongly favor the statement that human beings are simply not the cause of global warming, it's natural cycle of the earth. You see my point, right? So if you really want the wisdom, or you want the truth to emerge, you want to take intelligent people who are making, but not necessarily pundits. You want to take just intelligent people who are capable of thinking on their own enough just more than 50% right or sense in them. And then you take a collection of them and you'll be surprised at how uncannily right they are generally, right? So the basic ideas are you need weak learners, you need a lot of them, and then comes the other aspect of it. See, what happens is if all of them are reading the same book, they'll reach the same conclusion. So the way you ensure that the learners don't get correlated or entangled is in their learning is by giving them different windows into the data. So one metaphor that you can use is blind men and the elephant. So you have a big elephant of a data, but to each blind person, you blindfold them. And so each person gets to see and feel only a part, or rather feel only a part of the elephant. So one feels the trunk, one feels the ears, one feels the tummy, one feels the legs, and so forth. But if all of them are willing to agree that they are all correct, the picture of the elephant will emerge, isn't it? Or more prosaically, see, whenever you take a picture, a photograph is a two-dimensional representation of a three-dimensional thing. You take enough photographs of a thing, you will be able to reconstruct it in its full three-dimensionality, so long as all the photographers are not taking photographs from exactly the same vantage point. If they are all taking pictures from the same vantage point, you would really not know what is out there on the other side, right? Or on any side except the front from which they're taking the picture. So for them to collectively be able to reproduce the building in all its three-dimensionality, you need to take an ensemble of those photographs from different vantage points, seeing different realities, subset of reality. See, when you look at a building, you don't see the whole building. You see a subset of the building, the part facing you. And that is very similar to what you want to do. You want to give each learner only a subset of the features. So suppose there are 10 features there, you want to pick a small number of features, 2 or 3, and give it to them. So the way, if you remember, I motivated it was with the story of, or the metaphor of a teacher taking a bunch of school children to a special zoo or a meadow. In that meadow, there are only 2 animals, cows and ducks, right? Now, the teacher being highly scholastic, she begins to explain in intricate detail what are ducks and what are cows. So she talks about the fact that cows are big compared to ducks, that they have a swishy tail and big horns, right? And they have 4 legs and hoofs, and so forth. On the other hand, when she talks about the ducks, she emphasizes that they are small, feathery, webbed-feeted, beaked, right? Winged creatures. So you may speak a lot about the attributes of a duck and the attributes of a cow. Imagine that these children are all pre-kindergarten children, right? Or preschool children. You have taken them and you're explaining so much. What will happen is different kids will latch on to different attributes. One may remember, for example, that if it is big, it must be a cow. If it is a duck, it must be small. And she may also remember that if she sees a tail, it is probably a cow, right? Things like that. If there is no tail, then it's probably a duck. Some other child may latch on to the fact that webbed feet is it. Look at the feet. Are they webbed or are they hoofed? If you see hoofed, it's a cow. If you see webbed feet, it's a duck, right? Or she may notice that there are beaks. Is there a beak? If there is no beak, it's not a duck. So different kids in that crowd of collection or a class of kids would latch on to different pieces. Being little children, they're not going to understand all the anatomical differences that the teacher pointed out. And so now the teacher shows an animal and asks, what is it? Let us say that the animal is at a distance. Then to the kid who's looking for size, that cow may look rather small and may confuse it to be a duck, right? But let's say that the duck is flying around. The other child may happen to notice that it's a winged creature. It flies occasionally. And so It may come to the conclusion that it's a duck. So all of these children, they will come to their own conclusion between cow and duck using what they have learned. Right? They're looking at different subsets of the reality. But collectively, if you take the majority vote, you ask those children, what is it, cow or duck? Let's take the majority. Whatever it stands for, the majority stands for, you will notice that time and time again, that will be uncannily close to the right answer, right? And very infrequently, they will be wrong, whereas each child would individually be often wrong. And that is the point of ensembles. The other point, so that is your point C here. The point D is, not only should you let them look at different aspects of the reality, you should also let them see or learn from different samples of the data. Right? Because the data may have, any data sample may have some peculiarities. So just by accident, it may so happen that overall, the majority of the animals are white in color or something like that, or brown in color. Right? And so you might begin to draw conclusions like brown things are, or, brown things are cows and ducks and so forth, and ducks are not brown and so forth. But that may not be really true. So if you give subsets of the data, you sort of protect against an overall bias of the data. Right? So that's the point of giving different subsets of the data to different learners to learn from. So all of these things put together, those are our main 4 points. A, you need weak learners. You need many of them. You need different learners looking at different aspects of the subsets of the features. And D, you give them different samples of the data. Right? At the end of it, you want to make sure that the learners are not correlated. If they are correlated, then the bully feature becomes important. Right? So suppose there is one feature that always misguides. You see, the problem with decision trees has always been that if there is one, if you make your first split wrong, you get completely screwed thereafter. It's a fatal decision. The rest of the tree takes you down the wrong path. So, but then the root bifurcation that you do, you based it by scanning all of these axes. Let us say that one of the feature is dominant, and for whatever reason it misleads, because either the data is wrong or biased, whatever reason, and that feature always misleads. So what will happen? Your decision tree will always come out wrong. But if you create lots of decision trees, like let's take the example of decision trees. Those learners can be decision trees, but they can be anything else. Suppose you take a lot of decision trees, but to each tree you only give a few of the features. So what will happen is the majority of the trees will not get that dominant feature that is screwing up the analysis. So some trees will make a mistake because they got that feature. Majority of them won't. So I'll illustrate it with a number and an example. Suppose there are 100 features. It is a good idea never to give more than square root of the total features. Here, the total features are 100. What is the square root of 100? 10. So to each tree, you give no more than 10 features. So let us say that there is a bully feature and you create a few hundred trees. By the law of large numbers, it will happen that only 10% of the trees, 1/10 of the trees will get that bully feature. So 1/10 of the trees will get the answer wrong quite often, right? But then that's the beauty of it, because you're ensembling before you're aggregating the results of the ensemble. 90% of the trees will come back and give you the right answer. And so the bully feature gets muted, it gets suppressed, it gets neutralized. Do you see the point, guys? Huh? So that is it. Now, how do you take the aggregate? It's very simple. If you're doing classification, as we talked, you take the majority. If you are doing regression, you take the average of what they're saying. So you ask the children, like for example, I would ask you guys, how many stones are there in that jar? Whatever number you say, we take the average. You want to know what's the temperature outside? You ask all the children, what do you think is the temperature outside? and then you take the average value, and that's your prediction of temperature outside. Are we together? Right? So that summarizes what we have talked so far. Guys, please stop me here if you have not understood so far. Are we good so far, guys?
Good.
Magesh, did you follow any part of it so far? This must all be looking a bit strange.
Yes, Asif. Yeah, getting it.
You're getting it, huh? Very good. Anybody else has a question, please ask me. Otherwise, let's take, it's 8:30 now. Should we take a 15 minutes break and regroup at 8:45? Let's go get some water and so forth. And let's get together at 8:45.
Asif, I just wanted to ask you, when you said, we need a mechanism to keep the bullies who can dominate neutralize,
Yes,
is that the way when you gave only a part of the features to each decision tree? So is that achieved by that?
exactly. In fact, the rule is square root. If you
Okay.
have P features, never give more than square root of P. In fact, that is one of the mathematical theorems. It's a theorem about data projections.
Okay.
You just need square root of P at most features to get, there are words like, isometric embedding and so on and so forth. I won't go into the mathematics, but take it as a fact that it works.
Okay.
Right?
Thank you.
Behind all of this, I've given you the intuition, the gut feel, or the picture. Each of these are deep wells of knowledge, mathematical knowledge. So you can keep drilling deeper and deeper into it. It's a big rabbit hole.
Okay.
Asif,
Go ahead, River.
just want to make sure, just my understanding. This Gini index is giving like the proportionality, right? Of when it derives from there.
It's derived from proportionality. Both
Yeah.
entropy and Gini are derived from proportionality.
And ROC curves are also derived from proportionality, right? That true false.
ROC curve is different. No, it's about model metrics.
Okay.
It is about the precision and accuracy, or rather, a false positive versus true positive.
Okay.
So, in other words, as an aside here, ROC curve is, suppose you take a certain cutoff in the data, like, see, suppose you have a probability that it's a cow.
Mm-hmm.
Suppose you can say cutoff is half. If it is 50% probable, mark it as cow. Or you could have taken 1/4. Even if it is 1/4 probable, that's a cow, it's a cow. Or maybe you need a lot more assurance, 3/4. So you can, the probability X where you put the cutoff determines the rate of false positive and true positive.
Okay.
Right. So if you're not careful, see, a bad model, right, that is making random guess will have equal rate of true and false positive.
Yes.
Because it's clueless, right? But a good model will achieve very low, right? For a very low false positive rate, it would have already achieved a very high true positive rate, which makes sense, right? You want a good model that is a high true positive rate for a very low false positive rate. So this is the ROC curve.
Right. So if like after partitioning, if Gini index gets better, the ROC will get better, right?
Oh yes, of course.
Yeah. That's how they're connected, right?
Yeah, they are. In that sense, yes, they are interconnected.
Yes, whatever.
Yes, so yeah, that's a good point. Suppose this is your square box, right? This is a pretty bad baseline. You can actually do worse than baseline, but let's say that in your first split, you're getting an ROC like this. Then the second one will give you an ROC, like a better ROC. A third one will give you ROC like this, and a fourth one will give you ROC like this, and hopefully a very good model will eventually give you ROC like this. So let me mark it 0. So let me call it the first split 1, 2. After the third.
Okay. Impurities keep getting better and better, right?
Yeah,
Genies keep getting better and better. Yeah. Okay, that's an intuition.
Fire keeps improving. Right?
Thanks a lot. Yeah.
So this is your ROC curve. So this is a good observation, actually.
Yeah. Yeah. Just want to make sure. Thanks a lot.
This is.
closest.
All right, guys. If we are clear, it is already 8:36. So let's make it 8:50. Let's meet in 15 minutes. Huh? And I'll pause the recording for now, and we will restart the recording. So if you guys want to talk without worrying about being recorded, this would be it. Control Shift Alt H. Pause. Where am I? I'll catch up with you guys in a few minutes.
Hello? Are you guys here?
Yes, Asif.
No, I think we're waiting for us. So, guys, just one question. Have you guys formed any groups for this project? Asif has assigned us or not yet?
Looks like most of the guys, they want to do it, go alone.
Sorry, Abhijit?
I'm saying most of the guys looks like they want to go alone.
Okay.
That's why no one is responding to you.
Okay. So maybe so that's okay. I'm in the same boat. I just thought to ask it anyway.
Yeah.
So I
Makes
think
sense.
we are kind of maybe towards, because when we used to meet at support vector, it was easier to just go to each other and say, hey,
Right. Yeah,
you meet first 5 guys and say, here's my group.
Yeah. You cannot replace that online. No way.
So are you guys all based out of Fremont area, or I mean,
I'm from
Abhijit?
Sunnyvale.
Sunnyvale, okay. I live in Fremont. Just curious.
So, is this Mardil? You live in Fremont?
Yeah.
Okay. What's your background, Mardil?
I am. My background is in telecommunication, hardcore network engineering side.
Any experience with R and Python?
No. I mean, this is.
You didn't do any R and Python machine learning before?
No. I am not from any coding background.
Okay, I am in Fremont, and I have already I partner with Patrick. He's a doctor.
Okay, very good.
I have a healthcare background. So
okay.
We both, and I don't mind if you want to join us.
Sure. Yeah, I want to make sure that this discussion is happening.
So we both work together at the same office, and around maybe 5-6 o'clock, we are discussing our data sets.
Okay.
Yeah, Asif sir, people are having trouble making their teams, so I think you should step in and help them out. So me and Patrick already decided.
You guys have decided.
And Mardul is in Fremont, and he couldn't find any partner yet.
Who couldn't?
I was talking to, I was asking if we have formed any teams or not this time around.
Right.
So seems like there are some moments I can ask each of them. Yeah.
So but you didn't do any coding before in R or Python, right? None.
Yeah. Python.
Okay.
A little bit on Python, yeah.
So then, because Patrick is very efficient, and I don't go, I just like to run fast. So
no, that's okay. Yeah. So I will ping you or Patrick on Slack so we can discuss it.
Yeah, sure.
Let the class continue now.
All right, let me ask. Shankar, are you going to do the projects? Do you have the time?
I may not have the time. Yeah, I might try, but I don't want to get.
Okay. Anil, how about you? Are you planning to do the project?
Yes, I'm planning to do the project.
Nice. So have you picked your mate?
Yes.
Who is doing with you?
Shiva?
Me and Anil.
Okay, good. So you guys are formed and you want to stay as a team of 2.
Okay.
Okay. Pradeep, how about you? Have you formed your team?
Yes, sir. Prashant is there with me.
Okay, so you and Prashant are paired up. Dennis, you have paired up already with Glennis and Prachi. And Kate, you also part of the same team or you're a different team?
I'm right now on the team of Haripriya and Balaji, and we were going to add a couple other people. I don't know where Haripriya is tonight.
Okay, maybe she's not here. Harini, how about you? Do you have a team?
Yes, I'm with Balaji, Asif, Balaji and Jay.
Oh,
you're on my team too.
Okay.
Yes.
Okay.
Cool.
You guys are a team. Then, Mridul, do you have your team? Are you planning to do the project?
Yes. So I think that's. I was asking. I'll see if Sukhpal and Patrick, I can join them if they are okay with it.
Okay, that's that. Abhijit, how about you? Are planning to do you plan to do the project?
I will be a little bit erratic because of the work I have.
Okay.
I will. I mean, someone can tolerate me, to be my partner.
Be confident, Abhijit. We are all busy people. Time is what you make out of it. I'm sure that we are all needlessly sleeping 7 hours a day. We should sleep 3 hours a day. No, I'm kidding.
I don't mind, sir. Mardul can join us, but we will gonna just. I'm not going to. Me and Patrick, we don't, spend time like how we import, what is the meaning of this and that, quickly, because we already spent two semester with you. So I will just go jump into.
Magesh, you're new, so one of your first tasks is to go find your mate. You can form a team of at most 4 or 5, and we have a project. So those of you who joined a bit late, let me give you a primer on the projects, guys. We are doing the labs. Obviously, as you notice that the Monday sessions are very theoretical and the Wednesday sessions are very lab oriented and practical. But while we are picking up the labs, it is also important that we do a practical project, a capstone project. I've given you guys the problems for the project. Now, here's the thing. If you do the project and you do it well, complete the project and you complete it well, the bonus that you get is you get my recommendation. You get me as a reference for your either your job or your graduate school. Right? And frankly, more than that, you also get talking points for your interviews. Generally, if you have done a project, data science interviews become a piece of cake. Most of the interviews start with you having to describe what work you have done. They'll ask you to describe some good work you did. And it has to be non-trivial work. It has to be more than just a lab. Your project becomes a basis of conversation. You talk about your project. And as you talk about your project, you sort of gain their trust. They begin to realize that you have something to say. More than that, as you do your project and you put it in GitHub, or you put it in Kaggle and put it in the usual thing, and I would highly encourage you to make an article out of it for Medium, and I'll of course help you write that article, help you with the language and the verbiage and so forth. It gives you legitimacy in the field. Generally, you want to be in a situation in which jobs chase you. You don't chase jobs. right? You know that one of the easy ways to know that you are good in a field is when you don't have to chase jobs. They all the time keep chasing you. Right? So it is important to reach that level. That's how you want to be. You don't want to be scared, especially in this economy. You don't want to be a person who's scared whether I'll get a job or not, or whether I'll lose my current job, and so on and so forth. You want to be the person who's always wondering whether, just finishing a project and pondering what would be the next project you would do, because you have too many choices. And you get there, there's an old saying, success leads to success. Success breeds success, I believe, is the word. You need to succeed, and I'm giving you a chance to succeed at a project. We'll give you all the assistance, all the help. So go form your team, work hard, and succeed at a project. You'll have my full assistance. And then showcase it, and then take that as your basis for getting job interviews.
Asif?
Yes, please go ahead.
Did you share the details of the project on the Slack or?
No, I talked about it in the very first lecture, and I will talk about it. Let's keep it as a conversation point for Saturday. I'll review all of that on Saturday.
Saturday noon?
Yes, Saturday. Sanjay, you missed that part, is it?
Yeah, I was not on the Saturday call.
Oh, you missed and also I think you missed the first day, is it?
No, I was there on the first day. You talked about the project. Okay, I missed the 1 hour of the second day, not the first day, but maybe
Yeah.
that.
So remember, all those recordings are there on YouTube. One of you asked, where are the recordings? Maybe I'll take a minute to show you the recordings, guys. Huh? Let me go and show you. In fact, if you look at my screen, what you're seeing is actually the live broadcast happening on the Support Vectors channel of YouTube. So how would you go to this channel? It's very easy. Just go to youtube.com/supportvectors. Very easy to remember channel, Support Vectors. When you go to this channel, and you notice that the moment something is live, it shows we are live now. Then if you go here, so these are the latest uploads. For example, this is the quantum talk and so forth from yesterday. Was it yesterday night? Yes, yesterday night. We seem to be having a lot of talks. Now you see the weekly tech talks. These are the Sunday talks. The quiz sessions are put here, but I decided not to move forward with that too much. But the first one is here. Then there are 2 workshops we have been through. Some of you have taken my workshop, Introduction to Data Science. And then at the very bottom is the workshop recordings, Practical Methods in Data Science. Do you see all of these videos here, guys? The very first session, the river data set, session 2. So first session, second, maybe I should order it. One of the things I should do is put it in the right order. But if you go to this recording, you will see that one by one, it will play through all of these recordings. All of these are here. So I will just cancel it out for now. So how many sessions we have had? We have had 2 weeks, which means that we have had 4 sessions. And we have had this Python, then 2, actually every week we have 3 sessions. Actually, how many sessions do we do? If I'm right, we do 5 sessions a week, Monday, Wednesday, then we do a Python session on Sunday, then we do a QA session on Saturday, and we do the seminar, the weekly seminar. So we're having a total of 5 sessions every week. They are all showing up on different channels. For example, this latest Python session is here. I don't know if you guys noticed it or anybody saw it. Oh, there are 3 views. So only 3 people have gone back and viewed it. The river dataset, I noticed that 15 of you have gone back and reviewed it. The decision tree, last Monday's topic, 33 of you have gone and reviewed it. That's very good. The practical methods, the first and the second lecture, again, 30 and 41 views. These are all views I'm hoping are coming from you guys. So yes, you have been reviewing these videos. So do go here and watch these videos, guys. Are we together? Right? And remember, the channel is youtube.com/supportvectors. The name of our workshop series is Practical Methods in Data Science with GCP, Python, and R. So go down. Maybe I'll pull it to the top, but I deliberately kept it to the bottom because it's not of much significance to the general public. Also, these videos are here temporarily. I'll take it away, I'll make them private, and only registered students will have access to it. Like, in other words, all of you who are here will have permanent and forever access to it.
Wow.
So you can forever keep going and reviewing it as you see the need for it. Right? Just like for Introduction to Data Science, those of you who registered for the workshop, they don't just see 3 of them. You should be seeing all 18 of them in your library. 3 of them I've made completely public, just as to give people a flavor of what the introductory workshop was. And Magesh, for you, did you get a sense of it? Now, if you go, do you see these lectures at the end?
Yeah, now I got it. So I will go through them.
Yeah, do please go through them. Huh? And one of the things I'll do after this class is I'll order them in the right order, because
Yeah,
number ordered by number one. Yeah.
Week one or like a date or something, because I think 15th and 17th you had, or so I don't know which day, so something like that, or the orders.
Actually, for me to order it, I can order it right now before we start. Playlists. Recording, edit. Let me fix the order right now. Yeah, there we go. So I need to just move it up. Now it's in the right order. First session, second session, decision tree was the third session. This was the fourth session. So that covers the 2 weeks.
Okay.
Right? This is Python informal session 2. I'll also put the Python informal session 1. And now they are all in the right order. Right? So just watch them.
Hey, Asif?
Yes.
Python informal session 2. So there is a Python informal session 1 also there?
Yes, I just realized that I haven't uploaded it. See, what happens with all of these videos is I try to make at least some effort to clean out the gaps in time. You know, the break, for example.
Yeah.
It's a 15 minutes break. It's worth removing it. So I do those things and then I post it. And of course, if you look at this video, for example, if you look at this video from the beginning, you'll see that I would have, this is the raw recording. Right? Just make sure that everything has come through clearly. And sometimes you'll notice that I'll add, for example, here, I'll add a little bit of a preface to it. Right? Do you notice the support vectors banner and so on? But this is, just think of it as a show off for
editing, movie editing.
Yeah, movie editing, a little bit of editing to that. These are bragging rights, you know, this is how you create brand awareness.
Asif, I don't think so. We recorded Python 1, series 1.
No, we did actually. We did.
Okay.
Have it. It's just that unfortunately I also stay very busy, so I don't have time to, which is one reason. So it's a chicken and egg dilemma. You know, when you have a one-man operation like this. Last year we had a pretty good revenue, and this year I was going to start out by hiring an executive assistant, a secretary. But then came COVID and all our lives upside down.
COVID destroyed everything.
It destroyed the revenue stream, of course. And in a way, see, everything has a silver lining. One good thing is that I'm taking the virtual classes much more seriously than I used to before. But the point of the matter, the unfortunate thing is, the revenue stream is much lower. So I can't get the executive assistant. I really need to do these things. See, after I finish the class, somebody should just help me upload all of this, right? And I don't have that. There are people who are helping quite a bit. For example, Prachi is helping a lot, but already our hands are full. We need somebody who does the editing. Editing takes a lot of time. Each video, like suppose I give you guys a talk of 3 hours, it takes me typically 1.5 hours to edit and clean it out before posting it. So it's the nature of this, and help in that someday with the assistant would be good. So there we are.
I can do it, Asif.
Prachi, you already are doing a lot.
But still, like...
No, I can do it.
Yes, I can help you. I mean, I can definitely get you started. It's a good skill to have.
Yeah.
But I fear that you're already busy on a lot of fronts. But
that's okay. It's something to learn about. So, and even Dennis said, so we both can do it. And like,
Okay.
I can do that.
I can also help Asif.
Even Dennis can do it. See, which means that they're meeting, I think, in the
Nice, guys. If you all help, of course, then we can make sure that as soon as the lectures are over, we clean and post it.
Yeah.
Yeah, see, this is Abhijit again. Going back to the project, right?
Mm-hmm.
Do you think tackling those projects by oneself is a good idea, or it's a good idea to have, I mean, from a workload standpoint, it's a good idea to have at least one partner?
You know, have you, so the best advice I can give you, and this is, by the way, my personal advice, is I follow the reverse Fibonacci series. If you take the numbers, right, 1, 2, 3, right, 5, 8. So the basic rule is, if you are, when you really are a novice, go join a team of 5 or 8, right?
I don't know if there is any.
Because you watch how they do it and you contribute in wherever you can. You were doing that, if you remember, in the boot camp.
Yeah, I could not complete it. Yeah.
Then after that, a step down. If you are in a team of 8, go to a team of 5. If you're in a team of 5, go to a team of 3. If you're in a team of 3, go to a team of 2, right? And try to do the next thing with a smaller and smaller team, and then go solo. If you go solo right away, there are two demerits, multiple demerits to it. First is that you will get stuck and you will struggle, right? Number two, every day we have pluses, you know, days when we feel at times, or hours when we feel motivated, and then hours when we feel a slump, right? So for example, Abhijit, you and I both come from the same region of India, Northeast. So right after a nice dose of gulab jamuns, we feel quite happy. We are ready to conquer the world. But right after our heavy meal, we slumped. We don't feel like doing anything. So you'll have your ups and downs. So then the point of a team is it sort of integrates or average over is when you are having a slump, somebody else is motivated and making progress. And also, again, the same wisdom of crowd comes in. We just talked about it. A lot of you working together have different ideas. You have different strengths and weaknesses. And so a collection of weak learners leads to a very powerful team. And so I would initially suggest, do not be shy, go join. You know, one advice somebody gave me in life is that in the early stages of your career, you should only work in teams where you have a guarantee that you are the dumbest of the lot. Right? Never work in teams where you're the smartest guy, because then you won't learn anything. I don't know. This is a career advice we always give to the young. Right. And then gradually as you mature, you know, if you can survive, you may be the least knowledgeable person in a high powered team, but the high powered team will teach you a lot. Right? That sort of mentality. So you should never feel that, oh, you know, how will I look lousy or something. Join a high powered team. And
I don't know where is that high powered team, how to find the high powered team here.
Yeah, here I would say if you want to join the high powered team, who just find out who are the people making most progress. Right? At this moment, almost everybody is more or less at the same level. Some people are at a slightly better level than others, but there is no exceptionally high-powered people. You all are capable. You all can do it. So jump into it and make progress. And so anyway, that's my advice on going solo versus being in a team. Start out in a team, and then in your next project and the next project, shrink. And at the end of the day, you'll become a lone wolf. You know, you'll run your own thing.
Asif, I'm also looking to join some team, but I'm not sure which team.
Yes. So remember that you want to join any team is good, which has a mixture of talents. So don't join a team. Let's say that if you're completely new and you have been doing some analysis, Bhuvna, isn't it?
Yes. Yeah.
Then you pick anybody in that. Who would like to join Bhuvna, by the way? Abhishek, do you have a team member?
No, I don't have any team member yet.
Bhuvna, would you like to join forces with Bhuvna?
Yeah, I am fine.
You guys join. Anybody else? Let's increase the team size by 1 or 2 more. Anybody else would like to join this team?
Yeah, I can join us if I'm Aditra.
Aditya, yes. So there you go. Bhuvna, Aditya, Abhishek, 3 people. 4th person, Abhijit, you want to join? All right, that makes 4 of you.
If these people, I hope I am not forcing myself on them.
No, there is nothing like that. See, remember, guys, I'll be helping you and making sure that you don't fail. I'll also be giving you guys starter code. On one of them, the archive project, I'll give you the starter code. Huh? I'll give you a notebook that gets you started. When will I give you? I don't know, because I'm very busy. As you can imagine, we are already holding 5 sessions a week, but I'll find time to give you guys that. All right.
So Bhuvana, Aritra, myself, and
Pradeep, you have a team member?
Pradeep is sleeping, sir.
Pradeep is sleeping. Okay. Sonal?
No, I am not.
Do you have a team member?
Yes, sir. We have 2 members. 3 of us are in team.
How about you, Kamya? Kamya, do you have a team member?
I do not. I do not.
Pick a team member quickly. Who would you like to pick? Who would like to join forces with Kamya? To give you a background on Kamya, she is in college. She is going to Purdue and has exposure to machine learning techniques. She could be quite an asset. Any team?
I don't have a team member.
Bhavesh?
Okay.
Yeah, there you go. And anybody else would like to join this team? Sonal, how about you?
Okay, but I'm not too experienced with all this.
It's all right. None of us are experienced. We can all join forces.
Okay, yeah, I can
Kamya,
join.
would you like to work with Sonal and who else was it? Bhavesh, yeah.
Okay.
All right, guys. Is there anybody who's still without a team? Balaji, you have a team. I think everybody else here has a team, isn't it? Kala, who did you join forces with? Are you a team of one or
No.
you have some people?
No, I'm not. I'm not because of as if I'm repeating the course, right? I'm done all these labs almost.
Oh no, it's not the labs, it's the project.
Oh, for the project?
The COVID project and the archive project.
Okay, okay. No, I don't have a team yet. No, I don't have a team yet. I was going to ask Anil if he wanted to join because I know Anil from before, and anyone else who wants to join is fine.
Anil, you have a partner yet?
Yeah, so I'm with Shiva.
Okay, so Shiva, would you like to take Professor Kala?
Yeah.
Okay, so the three of you guys are a team now. So all right, anybody else who's left behind? Mridul, you have a team? You do. You were just talking about, yeah.
Yes.
Prachi, how about you? You, Glennis and Dennis are a team. All right, guys,
yeah.
is there anybody left behind? Sanjay, how about you? Who do you have?
Asif, can you hear me?
Yes, Sanjay, go ahead.
Yeah, so me and Saurabh, we are doing together.
You're doing
I was chatting with Sukhpal. He's also doing with somebody else. They are 2 and we are 2. So trying to see if we can make it 4 together. But I'm not yet sure. Me and Saurabh, we are together for sure.
Okay. I have a user showing here as Aro. Who is Aro?
Roc Khanna, sir.
Who is that?
Roc Khanna?
I want to know.
That's a good one.
Yeah,
It's
Aro.
true.
Srinivas.
Well, you don't know basically these days, right? He's in politics also. There's a lot of machine learning goes on.
Yes. Aditya, who did you join?
I haven't joined anyone yet. No.
Would you like to join Sonal and Kamya and Shiva?
Wait, do you mean Bhavesh's team?
Yes.
Yeah. Okay.
So pick a member, pick a team. And Jaya, do you want to do the project? Would you have time?
I'm doing that inside thing now.
Right.
So, yeah. So, but I'll be there for 2 more weeks. Then I will see if I can join some team.
Srini, how about you? Do you have a team member, or are you intending to do the project?
Actually, I have decided to go with my previous team. It's Pradeep.
Asif sir, we are in the same team.
I think we have solved the pairing problem now, hopefully, right? All right, let's move back to our stuff.
Ask a question for you. If people are doing in pairs, if Anil wants to do with whoever, that's fine with me. Is it okay if I can do solo? I can ask Sandeep for help?
That would be a great team, mom and son.
Yeah.
So
he's not following this class per se. He's not.
Okay.
But
so he can help you with the project, Kala. That could work for you.
Yeah.
And so the only limit I'm saying is no more than 5. But solo is definitely good. And especially with Sandeep, it will be great experience for Sandeep also.
Yeah.
That COVID data, by the way, you know, the project that Sandeep is doing, it directly relates to that.
Okay. Okay.
I've given him the project to work on graphs for COVID.
Okay. Yeah.
So it's very pertinent.
Sure.
Excuse me. I have an air conditioner in my room which doesn't have a thermostat. So either it is warm or it's too cold.
Okay. What are your expectations with the COVID project? You're going to give us some kind of outline.
Yeah. So here are the 2 projects. Let me summarize the 2 projects. One project is there is this archive data. So archive is archive, right? All the research papers, preprints go to archive in every field, especially in the mathematical disciplines like physics and so forth, and computer science. Let me show that. Let me give a review of what I said. What are projects? Maybe I'll do a write-up and put it here in a day or 2. But
yeah, that's what I was hoping for. What your expectations are with regard to what you expect to see in the project. Some kind of a rubric, and this is how I'm going to grade your project.
Do you see this archive? This is where all the papers are published, right? So for example, if I were to search for myself, you'll see some papers are published here, right? Or if you were to look at anybody, let's say yesterday, Dilip Krishnaswamy was our speaker. By the way, you missed the talk on quantum computing.
Yes, I did. Yes, I did. But then I followed the video today. Yeah.
Okay, I don't know why only 3 of his papers and only 2 of mine show up. He has produced over 100 papers. Oh yeah, now they're listed. Okay, something is weird here. So this is it. So these papers all papers these days get submitted to archive. So now there is in Kaggle a data set. You can take it from Kaggle or you can take it from any graph website. Let me just look at archive. This is like data set, archive data sets. Okay. This is archive and date view by data sets type. Can reply to archive data sets for 2,400 papers. There is a bigger one for. Okay, I'll paste the data again. It's in gigs. So you have a lot of. Maybe let's start with this, just to give you an idea of what it is. Suppose you take a data set like this. It's a data set of topics, 31,000 paper metadata plus. And each of these papers, it contains, if you look at this, do you see that it contains the summary? Every paper will tell you who the authors are, what the summary, the abstract of the paper is, what the title is, the year of publication is. But more importantly, it will also tell you the references in the paper somewhere. It should be there. Okay, so author, title, and so forth. Not in this particular one, in another one. It will also tell you the references, right? What are the references? What other authors they are referring to, and so forth. So anyway, you take this. Now, with this archive data set, you can create multiple kinds of projects. You can make a graph, right? Looking at the graph relationship between authors. So one author cites another author, or you can create so that's a citation network, or you can create a citation network of papers. One paper cites another paper, right? So you can create a network and then look for structure in the network. That would be one thing. The second is you can take the abstract of all of these papers and then try to do natural language processing in it. And can you just from the abstract classify it into different topics? Just if I were to give you a few sentences from the abstract, would you be able to tell which area? Is it computer science, machine learning of computer science, or is it theoretical physics, or is it, whatever it is, the area of the paper? So you can do all sorts of different projects out of it. Pick an idea, propose that this is what we want to do, and go ahead and do it. That's it. Any simple thing, but do it such that there is good machine learning in it, and you'll pick up some area. Make a graph, or do statistical analysis. Start with basic data exploratory data analysis, see how far it takes, and then do something, make a graph, do something.
So we have to do one of this, like linking and topic, or both of this?
The more the merrier.
Okay.
Yeah, see, the more you do, right, the more practice you get. The whole point is that this field, this subject of data science, there is a theory part of it, which is important to understand. And there's a practice part of it. Practice is like tennis, no amount of watching the great champions of tennis on TV helps. You have to get onto the field and do it. So that's the doing part of it. Let's go do it. All right, guys. So we are running a little bit behind. I was going to, well, it's 9:30 already. I don't know how much I should teach now, but let me give you the big ideas. I will finish the something called bagging and boosting today. I'm going to start the recording now, guys. Huh? 1 second. So we'll talk about the concepts of bagging and boosting. These are two important topics, right? So we'll talk about this, except that today we'll limit ourselves to bagging, right? This word bagging is actually a combination, or what's the word, portmanteau of two words, bootstrapping.
Compound.
Say that, Kate, again.
Compound.
Compound, yes. Bootstrapping and aggregation. Well, it's an often interview question that people ask, what is bagging? See, usually people don't know, and sometimes even interviewers don't know. They just talk about the mechanics of it, but it is actually the compound of these two words, bagging, bootstrapping, B-A-G. Do you see that? Bag. So what is bagging and what is bootstrapping? One way to, let's talk about bootstrapping. What is bootstrapping? Bootstrapping is, and I'll give you a very rough idea. I won't go into the formal definition at this moment. So suppose you have points, data points. Let me mark these data points with a certain color. What color would suit us? Let's go with this color this time. So suppose you have a data points like this. And this is the sum total of your data points. And you want to generate training data out of this and give it to one of your learners, right? So I told you that don't give the same data to each of the learners, right? What you should instead do is pick a different subset for each. Pick a different subset of data. So for example, to one, you can give this data. To another, you can give this data. To another, you can give this data. To another, you can give this data. Do you see that? Right. And you realize that different people, different sets, different samples, let me call it I, J, K, L, M. So sample I and sample, any two sample given I, J, sample I, intersection sample J, is not necessarily null. In other words, samples may have overlapping elements. Are we together? And you obviously take random samples. So this process is bootstrapping. Are we together? This is bootstrapping. And I'm giving you just the whole flavor of the whole thing at this moment. Let's go with that. So far, so good. And nature of bootstrapping is, some people will say, you take a sample and then you replace it back into the bag. And then it's like, you know, if you have peanuts in a jar, you put your hand in the jar, you shuffle and you take some peanuts out, look at it, and then you don't eat it up, you put it back. So that the next time you again put your hand in the jar and you take another bunch of peanuts out, and some may have belonged to the first time you took the peanuts out. So that is bootstrapping, roughly speaking. Then there is aggregation. Aggregation is much simpler to understand. Aggregation. Aggregation is, simply put, just for regression, take the average prediction from each learner, and for classification, by the way, guys, is my handwriting reasonably legible? Are you able to read it? Or it's too
Yeah.
squiggly?
It's okay.
And for classification, take the majority. So for example, if you have vote of the learners. So for example, if the learners are little children that you have taken to the meadow, you look at an animal and you ask each child, is it a cow or a duck? And now look for the majority answer, right? And let us hope that you took an odd number of children, so you always get a clear majority. In the same way, if you're taking regression, so suppose you're asking them, for example, for the temperature, whatever their prediction of temperature is, one child will say it's 72 degrees, another will say, no, it's 60 degrees, another will say it's 80 degrees, and you're asking them to predict the weather as it would be, let's say 1 hour later, right? So they will all make their predictions, take the average of the predictions, and the average is the correct answer, is the answer that you use. You say that it is the answer of the ensemble or of the crowd. The crowd has answered, and the crowd says the temperature is likely to be 80 degrees. Right? So do we understand aggregation also now? Right. So these two put together makes bootstrapping. Sorry, not bagging. Bagging is bootstrapping plus aggregation. Did we get that? Now, that is bagging. Boosting I'll keep for the next time, but let me mention a very popular algorithm that uses bagging. It is called, can somebody tell me what it is called?
RandomForest.
RandomForest. And its close cousin, which is slight improvement, but somewhat lesser known. There are many variants of it. For example, there is extremely randomized trees, etc. But let's go with RandomForest. So what are RandomForest? RandomForest is, the criteria is the learners are the trees. right? B, take lots of them. Take or create lots of learners. My basic rule is I start out at greater than 100 and I go up to typically, based on that situation, 400 or sometimes 1,000. Like lots and lots of learners. We live in the world of computational plenty. Go at it. Huh? The second thing is, see, to each learner, tree learner, give a bootstrap sample of the training data. Don't give it the whole data, give it a bootstrap sample of the training data. By now, can I assume we understand the word bootstrapped sample? Just to remind you, this is it. This red thing here is the bootstrap sample. Randomly go pick a small sample of the data. Right? The next thing is not only that, right? Let the a feature space be RD, i.e. R, not D, let me make it P. Suppose there are P features. P, there, B, P features. P can be 5 or 10 or whatever, 100 features, P features. Let the feature space be then give to each learner only a subset, let me call it S, which is much smaller than, obviously, than equal to P of the features. So you can give it, all the features to the of the features, but ideally less than P features. That you see, the random forest algorithm doesn't put a restriction, but math says, right? And I won't go into the math. There's a whole random projection theorem. But I'll just leave it as a more intuitive word. Just say that the wisdom of math says, S should be less than actually the square root of P. So I'll just leave it S of the features. The math says, yeah, S of course, maybe so. P of the features, but actually you should not take. So for example, if there are 100 features, what is the square root of 100? 10. So take only 10 of the features. That's it. And then you build the model, and then the last thing is aggregate the results. Let each of the models be trained. Let each of the learners learn in parallel to build a model, to each build their decision tree models right? Then for inference, let each tree learner make its own independent prediction, make its own prediction y hat, right? So each of them will make their own independent prediction, right? So let's say that the learner is L and you're making a prediction on the data set I. They will all make their own prediction, right? And the last step is aggregate the predictions to get an overall prediction. To get an overall prediction. So this is a sequence of things, you know. What have we done in random forest? Let's look through the steps. We are saying you take so you need to pick some learner. In random forest, you use trees, which explains the word forest. What do you call a whole bunch of trees growing next to each other? You call it a forest, right? Now, I'll explain the word random in a moment. So now you create a lot of trees. Obviously, for it to look like a legitimate forest, you better have a lot of trees. More prosically, you need a lot of learners. So you need an ensemble. So this is your ensemble piece. Ensemble. Once you have the ensemble, now what happens? To each ensemble, you need to give it data. Each tree, you need to give it data to learn. Give it a bootstrap sample. Don't give the entire training data to the tree. Once you have done that, now what you do is even from that sample, you don't give all the features. You take a random projection of the features. Right? So the word random comes from that, a random subspace. Random is a random subspace of the data. Subspace or projection. So the random in random forest is not that you take a random sample. That would be bootstrapping. It is the random projection that you do, or the random subspace that you pick up of the features, or the feature space. Huh? That's what you do. And so do you notice that these words, they sound rather formal when they're written in textbooks, but they actually have a very simple interpretation. Now, all of these learners, there's no reason they need to wait on each other. So they can all learn in parallel. In fact, they better learn in parallel. The more unaware each is of the other, the better. You don't want them to get correlated. And finally, you draw an inference. Let each tree, so suppose you want to make a prediction on a data. You show it an animal. Let each of the tree tell, is it a cow or a duck? And then you take the majority. Or if you ask the tree to tell what temperature is going to be tomorrow at noon, let each of the trees make an inference, and then you take the average prediction. So that is the aggregation part. So you notice, guys, that we had to put a lot of ducks in a row. Right? We took the idea of ensembles, we took the idea of random projection, we took the idea of bootstrapping, and we took the idea of aggregating. So we had to put 4 ducks in a row to get this algorithm, random forest. It is a beginning of what our world is going to be going forward. If you have done ML100, and so far, you have been dealing with simple algorithms based on one idea. Right? Random forest is your introduction to a complex algorithm where you have to put many good ducks in a row to get a good algorithm. You know, many ideas come together, or strands of thinking come together to form the big picture, the big idea, or the full algorithm. It has many good components to it. Random forest, the limitation of random forest is, it is a black box model. If you ask a random forest, why are you making those predictions? It will just shrug its shoulder and say, well, I like to make that. That's what I learned. Now, what exactly did you learn? It won't be able to tell. It's a black box model, right? All you get is the X vector goes in as input, and Y hat, Xi goes in, and Y hat comes out as a prediction. Are we together? You can't open this box and ask, what is there? How is it making the prediction? Explain it to me, right? It is not a model that has a parameter. That's why I say it's a non-parametric model, right? It's too hard. You cannot say that there is beta naught, beta 1, beta 2, and so on and so forth. And so these are the knobs I can use to explain to the user why the machine made that prediction. It's quite a loss to be able to lose interpretability. So it degrades into. So interpretability is a big sacrifice you make. Sorry, I pulled that word. Interpretability sacrifice. Quite a bit, but not completely. There is one silver lining. So we better take a silver colored pencil, I suppose, for silver lining. Is this silver colored? Looks like it. Silver lining. I'm joking, guys. Silver lining. So there we go. We have a silver lining. Silver lining is one thing that you have in linear models or straightforward models is interpretability. You can compare the size of the coefficients and get some sense of how relatively important each feature is. That is preserved. Feature importance the relative importance of features. Rough global average level is preserved. Now, I used a lot of words. Let me explain it. Rough global average level is preserved. But forget the rough global average word for a moment. It will tell you that suppose you're talking about diabetes, and let's say weight is a factor, age is a factor, right? And weight or size of the person. And maybe the two put together make a BMI, but let's skip that. And your age and your and a few other factors, genetics, and so on and so forth. And you're trying to determine, given all those factors, is the person likely to be at risk of diabetes or not? At risk of diabetes. And when you build a model, let's say that you successfully build a model in which Xi goes in and you predict at risk, true, false. Then this model, this random forest that you have, you can ask it that in making the decisions, how important were each of these factors, each of these affective contributory factors, weight, age, size, etc. So it might come back and say that, hey, you know what, let's say weight matters most. Weight matters most, and then is greater than age. Let's just say, I'm just putting, I don't know, a doctor may disagree. So size, genetics, I don't know what the right order globally would be, something like that we put. But there is a problem with this. Random forest gives you that. The trouble with this is that it gives you sort of an averaged out feature importance. That on the whole, this is what it is. It doesn't capture the nuances of prediction. So for example, when in different regions of the feature space, for example, this region of the young people, what happens? A lot of background sound. If you can please mute yourself. Okay, so suppose you're looking at the young people here, then for the young, as you know, unless you have type 1 diabetes, so let me just make it type 2, adult onset type 2 diabetes. So children tend not to have type 2 diabetes, right? Even if they are relatively overweight, they tend not to have type 2 diabetes unless there's a genetic predisposition to it, right? So you might say that for young, genetic factor is here, genetics is overwhelming, is more important. But Even, but as a general population, you may agree that for people who are older, over 40, greater than 45, now suddenly what begins to matter? Weight and size, of course, together making up the BMI matters. And let me throw in exercise here. Exercise matters. Exercise matters. Things like that, they begin to matter much more. Right? I don't know. Medically, I'm quite likely to be off, but I'm just using this to illustrate a point that in different regions of the feature space, or for different age groups or different weight groups. So, for example, if you take all people over 45 and the same BMI, now all of a sudden genetics will begin to matter a lot, or the level of exercise will begin to matter a lot. So, feature importance is actually a very complex and nuanced topic. And it is almost very poorly understood by most people doing data science. They don't understand the sheer complexity and nuances of feature importance. So anyway, I'll stop today with the statement that whenever you talk about feature importance, and even when you read these books by all these publishers, they actually they can be quite misleading. They will tell you that in RandomForest, etc., you have feature importance coming in. Remember that those are very rough measures, global measures. Feature importance is a deep topic. And whenever you look at feature importance, so for example, a given user, suppose a user is, a person is 25, right? The person does, like at that particular moment, what do you think is the risk of diabetes? What is more likely to cause it, right? There are multiple things. You know that the young people are active. They're on their toes always. So you'd probably advise them to be careful about their diet. Right? On the other hand, as people get older and older, their exercise level goes down, but their food habits remain more or less stable. So now you want to emphasize, well, they're not likely to suddenly start overeating, and assuming their food habits are reasonably modest, now you want to start emphasizing exercise, right? Because people become sedentary as youth fades away. So things like that, what you advise or what factors matter more, is like asking that how much does Y change? It's something as that, you know, if Y is a function of X, how much Y changes for each of the individual predictors in a for a given value of the X vector, right? So it's a local feature because you're essentially comparing, roughly speaking, the partial derivatives in the local region, right? You're looking at the gradients locally, gradient of Y with respect to each of these features locally. So this is getting a little mathsy, forget about that. But just remember that while people extol the virtues of feature importance in RandomForest and these models, take it with a grain of salt. Feature importance is more nuanced. Those of you, I noticed some of you are here after having done my boot camp last November, December. So you would remember that we devoted an entire day to the nuances and nuances of feature importance. And it also goes to the heart of something we are trying to do these days, recover interpretability of black box models. So, but anyway, this last part, by the way, is out of scope. So if you, I just gave you a teaser for things to come later on. If you didn't get the whole thing of it, don't worry at all. The only thing you should take back is the feature importance is there in a very rough way in RandomForest. RandomForest is a complicated model. It is built out of you need to line up at least 4 ducks in a row. You need to use the concept of learners, ensemble of learners. Those learners should be weak learners. You make them weak by giving them a random projection of the data, right? A random data projected to a subspace of the feature space. You give each bootstrap sample. Then finally, you aggregate the results. All these things are efforts to make sure that the trees or the learners are decorrelated, right? That's what you do. Now, one remarkable fact about random forest and a dirty little secret is, I said that number of features should be less than the square root of p. Now, here's the dirty little secret. Quite often, if you create a forest in which each tree is given only randomly one of the features, those are called stump trees, right? Stumps, a forest of stumps, no branches. Right? It performs remarkably well. Quite often, it performs as well as a more complex tree. Are we together? Right? So that is it. So that is random forest. What it addresses is this tendency in decision trees to fit data hard, to go and overfit to data. Decision trees always had the problem of overfitting. People did all sorts of clever pruning algorithms. And then came random forest. And then random forest created quite a tremendous debate in the community. People asked that machine learning used to be not just about making predictions, but about interpretability or providing some inference about what happened. Why is it happening? You lost that, you lost interpretability. Was the sacrifice okay? Today, we of course say that it is on a case-by-case basis. Right? Sometimes where only performance matters, you want the best model that you can build. So for example, if you want a self-driven car, you just want it to perform well and keep you safe and keep the other people on the road safe, right? Prevent accidents. You probably are not too concerned on what the interpretability of its decisions are. You just wanted to make the right decision, right? But on the other hand, in many other situations, for example, if you're trying to give a job based on algorithms and how people performed on a test, you want to make sure that the models are highly interpretable. You're not willing to take a black box that says, like an oracle, that, all right, this guy is better than that guy. So take this guy, don't hire that guy. Because there, interpretability of paramount importance, because there may be biases. If the data is biased, your machine learning algorithm will be biased. And a black box model, you will not know easily that there is a bias in your predictions also, because there was a very subtle bias in the data. In fact, companies have been sued for doing this. In US, you can get sued because we have the protected classes. You need to guarantee that you don't discriminate against the protected classes, race, gender, age, disability, and so forth, right? And so in the history of this is, without taking names, there was a company, a big company that was sued because it could be demonstrated that it was discriminating against the protected classes. They claim they're not deliberately doing it. They're feeding all the data they have into the algorithm, and the algorithms are blind and impartial, and so they are making predictions, therefore it is right. The judge did not quite agree. He says, no, it doesn't matter. The fact of the matter is there's evidence that your process is creating discrimination, is doing discriminatory hiring. Therefore, the circumstances of how you produce that doesn't matter. You're responsible for the wrong decisions. Right? They lost the case and they had to pay a lot of huge penalty. So obviously in these situations, now you ask why it happened. It had to do with the fact that the data had inherent bias. The algorithmic training had bias, therefore. All of those things creep in. So there are situations where you can use black box models. There are situations where you cannot. And nowadays we are entering a world in which we are saying, well, we cannot but help use this very complicated black box models, right? Deep neural networks and so forth. But we want interpretability nonetheless. And so we are trying to create a whole new wave of body of research and tooling and stuff to restore some semblance of interpretability and explainability on top of black box models. So that's a very promising areas. Those of you who did the bootcamp with me will remember some of it. And in the next bootcamp, which is in deep learning, it will become a topic of paramount importance. It's also a very hot topic today. So with those words, I will end now. Any questions, guys, on random forest before we close the session today?
Yes, sir. So in random forest, every tree is decision tree, right, sir?
It's a decision tree, yes.
Asif, is there a recommended sample size to do random forests?
Generally, it will do the right thing internally. It will look at your training data set size and it will pick a sample size. The basic rules of sample size is, you try to take a reasonably big sample, but you make sure that you don't take the whole set itself. Right? And, suppose you have 10,000 points and what's a square root of 100? So long as you're taking more than 100 points or so in a sample, it's good. It's a good sample.
How does random forest deal with high correlation between features?
It is actually very good. Let's say that the features X1 and X2 are highly correlated, right? The beautiful thing is one tree will get only X1, another tree will get X2. So you don't have the problems that you have, the pathologies that you have in linear models.
But doesn't it overcount the effect?
So what happens is that the beautiful thing happens is that when you ask for the importance, it will ascribe equal importance to X1 and X2, because some trees will be using X1, some will be using X2.
Okay.
That's how it is. So the problem of multi-collinearity, therefore, is moot when it comes to random forest. That was one of the big reasons people, when random forest came in, they were a runaway success. Everybody
As if we lost you.
was using it. You go to Kaggle and use trees, boosting. You hear of all this cat boost, XG boost, and so on and so forth. And we'll talk about boosting the next time, next Monday. Remember,
I'm not sure if everyone heard a little bit of gap of what Asif was saying, or it was just me only.
Guys,
No, it was for everyone.
Yeah, audio was dropped, I think.
We lost you in between, Asif.
Oh my goodness. Okay, so I'll say that again. What I was saying is that a lot of the if you go to Kaggle and you look at the winning entries for tabular data competitions, wherever data is tabular data, not image or sound or text, but the simple tables of data, you will often find that the winners are in the leaderboard. You'll often find entries of teams that are using one of the ensemble methods. They're using random forest or gradient boosting, this cat boost, XG boost, whatnot. They'll be using things like that. Very, very often you'll see them. You'll see at least some entries in the leaderboard coming from this. So this is a very popular algorithm. Obviously, like with every algorithm, people do get carried away. There are people who solve every single problem using a random forest. Right? So that's that. Actually, it reminds me of something very interesting. My good friend, Dilip, who presented in quantum computing yesterday, he and I used to have a joke. So he would say that we have to write code. So he would say, wait a minute. He would open the code editor, write int ij, and then he would say, now tell me what the problem is. Because he would always need the variables ij. It's like that. So nice, after all these years, when I think of random forests, it's like that. A lot of people swear by it. They'll say, okay, let me first instantiate a random forest, and then you tell me what the data is. And what should I fit to it? It's very effective. Right? And now we are entering the space of these powerful methods, very, very practical and very usable. And you use it a lot. Become good at it, guys. It will solve a lot of your problems. After this, we'll do boosting and its implementations, XG boost, cat boost, ADA boost, and all that. And then after that, we'll go to yet another very powerful idea called kernel machines or kernel methods. We'll do support vector machines and so on and so forth, right? So in this workshop, of course, we are moving fast. We are moving through rather powerful algorithms. Theory is done of this. Next time, remember, Wednesdays are for practice. We will do lab work in random forest. Lab work is an entirely different kettle of fish. You'll realize that lab is very easy. You just instantiate the random forest and fit it to data, right? But we'll learn to see its nuances. It's important to know some of the nuances involved, and we'll develop practice in that. Any questions, guys, before I end?
Fasil, just one question. This weak learner, right? Like in this case, you are showing them only weight or age, not everything. Subset of features, right?
Yes.
And they are doing prediction based on decision tree algorithm?
In random forest, yes. But in general, you don't have to. If you can create a bagging of anything you want, any other learners you want, you can make a bagging of, you could use logistic regression. So let's take this example. You want to do a linear regression. Remember, in linear regression, you have the fundamental problem that if there is multi-collinearity between the features, you're doomed, right? You will start seeing explosion of variance. You start seeing pathologies. Your models are very unstable and they exhibit, variance inflations, like very sort of a slight change of the data will cause them to build entirely different models. One easy cure, just take an ensemble of linear regressors. You'll be and give them a random projection of features. You will realize that lo and behold, that problem is solved.
So, but all of these learners are using same algorithm, right, to learn?
Yes,
okay.
that is so. But now I'll teach. Now the next thing I'll mention. Actually, you sort of anticipated where I was going. Eventually, you will ask this question: Why can I not mix a few decision trees, a few linear regressors, things like that, different algorithms? Why can I not do that? If I'm doing regressions, I can mix 20 different algorithms and instances of them. And likewise for classifiers, I can take a whole bag of classifiers, different kinds of classifiers, and do it. So yes, you can do that. When you do that and you create an ensemble of heterogeneous classifiers, you actually get very, very powerful prediction machines. In fact, that is one of my own dirty little secrets. In fact, hardly a secret, it's an open secret, because I keep insisting that everybody should do that. Never solve a problem with one algorithm. Use every good collection of algorithms and lots of instances of learners from each of the algorithms. Do the same process. Instead of trees, replace it with those with a heterogeneous bag of learners from of different algorithms. And when you do that, it is surprising how much efficiency you get, because the weakness of one algorithm is made up by the strength of the other algorithm, and so forth. And you get very good thing. So bagging is one. We can do boosting. And the third thing is stacking. Stacking is something that I find very, very useful. I'll stack predictions from different machines, right? Different learners. And then put a learner that learns from the predictions of the different learners. That is stacking. We'll gradually come to that. I don't know whether we'll do stacking in the practical methods, but we'll certainly do it in the boot camps.
I see. So here in random forest, when we say ensemble means ensemble of weak learners using decision tree. Okay, thanks.
Yeah, in random forest, I say, because the word forest is
forest
of trees. It implies. All right, guys. So this is it. I will stop the recording.
I have one question.
Yeah, go ahead.
So when you said heterogeneous classifiers or heterogeneous, algorithms, they are like the example you gave, right? So the 100 features, and then you have, let's say, 10 learners or 100 learners, like that, getting 10. So so you distribute those algorithms like equally among the learners. So let's say there are 10 learners and you're using 5, so 2 of the learners will use.
I mean, generally what happens is, in those areas, my experiences, and this is the experience. See, this is where, just like each artist has his own style, each data scientist will have his own rules of thumb and their own experience. My experience is I don't try to be very clever there. I just take a bag of learners and run with it, different heterogeneous learners, and run with it. I'll throw the same number of learners, but I'll make sure they all are doing their own random projections and bootstrapping and so forth.
Okay.
Generally, I try not to be too clever because in my experience, being too clever doesn't help. That's sort of micro optimization. All right, guys, any other question?
No, thank you. Have a good night.
All right, good night, guys. I'm stopping the recording and I'm stopping.